Well, good afternoon, and welcome to our live streamed tour of the universe from the California Academy of Sciences. My name is Ryan White, the Senior Director of Morrison Planetarium and Science Visualization at the Academy, and I'll be your host for today's tour. This is an opportunity for us to use the amazing OpenSpace software, which you're looking at right now, to simulate a voyage from low Earth orbit, which is what we're looking at right now here at the International Space Station. And we'll go all the way out to the cosmic microwave background, the most distant light we can observe in the universe, in just a little less than half an hour. So we like to start the tour here at the International Space Station, or ISS, because it's kind of human scaled. And you'll be able to see my mouse at different points during the program here as I pilot through our virtual model of the universe using OpenSpace. And the great thing is that the ISS is about the length of a football field, whether you're thinking of European or American football doesn't make much difference. About 100 yards, 100 meters long. And the individual little parts in here that you can see, these things that look like canisters, are large enough to have people on board. And of course, that's how high people travel up into space these days. Of course, 2 astronauts just returned safely to the US after an overly extended stay on the ISS. But the main point is people, human beings these days, travel about this far out into space. But we want to show you the discoveries of modern astronomy that are taking us way, way, way beyond where humans have ever traveled. Instead, what we'll do is use this digital model, this virtual model of the universe, to pilot through different parts of the places around us that will give us a sense of where we are in the universe at large. So what I'm going to do is pull away from our location here in the International Space Station, and it kind of looks like it's plummeting to Earth. That's actually not the case. Let me go ahead and fade up the orbit of the International Space Station, its trajectory around Earth. And as we pull far enough away, you'll be able to see that it's not that that the ISS is tumbling down to Earth. Instead, it's just that we are pulling away from its location. And so this is actually not where the ISS is right now. It's where it was about a day ago. But I liked this this setup for the shot as it moves from daylight into dusk. Across the northern U.S., if your geography is pretty good, you'll notice that you might be able to recognize the west coast of the United States. You'll also start to notice some interesting things, especially as some of this data fades in around the planet. You'll notice that little blocks of clouds sort of faded in and came up as we got farther from Earth. And that's because we're using real data for all of this. Not just for things far away from Earth, but for Earth itself. So you'll notice, actually, my mouse is right over one here, these kind of bright stripes that run down the sides of our planet. And that's because this is assembled from recent imagery of Earth. In fact, it's about a day old. The reason I went back in time a day is because that's our last complete image of Earth using various satellites that are observing our planet. And we stitched those images together to show you what Earth looks like, not quite right now, but at least a day ago. So if you were watching the Weather Channel yesterday, you might recognize some of the cloud patterns. But again, what we're interested in talking about are things much farther from home. So let me go ahead and continue pulling away from our location here, home, Earth, our home planet, home to everyone you've ever known, every person you've ever heard of, our planet Earth. And as we pull away, I'm going to add some diagrammatic elements. What I'd like to do is show the orbits of planets around Earth. So first of all, you'll notice this line, the orbits of planets around the sun. You'll notice this line connecting the lower right-hand side of the screen to Earth. And you'll notice this circle kind of around our home planet. That is the trajectory of our moon. Let's go ahead and actually just take a quick visit to the moon. The moon is about 240,000 miles away, about 400,000 kilometers. If you think about how far that is, I don't know, if you have a car for a long time and you drive it for many years, you might put 240,000 miles on it. But that distance is the farthest that any humans have traveled out into space. I mentioned that the farthest people travel now is out to low Earth orbit. But the US and China have plans to return to the moon, or at least to go to the moon. Americans would be returning, Chinese would be arriving for the first time with humans. But for now, the last time anyone had visited our own natural satellite, the moon, was back in the late 70s, early 70s. Late 60s and early 70s is when the Apollo missions took people to the moon. And no one's been back since, although, as I mentioned, plans are to return. That's the farthest any humans have ever traveled from Earth, about 240,000 miles, about 400,000 kilometers from home. And so as we look at that sort of the radius of that circle, of that orbit of the moon around Earth, you're seeing a radius of about 400,000 kilometers. And that's a big enough number, but we're going to be talking about much bigger numbers. So we're just going to introduce another kind of measuring stick here, and that is light travel time. So light travels at 300,000 kilometers per second, about 186,000 miles per second. And that means that it traverses this distance from Earth to the moon in about a second and a half. Now, those astronauts that I mentioned earlier took a little over 3 days to travel from that distance, but light traverses that distance in about a second and a half. That's pretty quick. So we can talk about a distance of a light second. And that's not a measurement of time, it's a measurement of distance, because the distance light travels in 1 second. Similarly, we can talk about light minutes, light hours, light days, and light years. And light years might be the most familiar term, but as we begin to see the orbits of our other planets in the solar system, you can now see our inner planets, Mercury, Venus, Earth, and Mars. The orbit of the moon around Earth is so small it's less than a pixel on our screen. We're looking at the inner solar system, and this is measured basically less than a light hour in diameter, much less than a light hour in diameter, actually. So the distance from Earth to the sun is about 8.5 light minutes. So it takes light about 8.5 minutes to travel from Earth to the sun, or vice versa. And you can compare that to that second and a half to the moon. So if you think of a second and a half, that's maybe a pause in conversation. Whereas 8.5 minutes, I ate my lunch pretty quickly today. It might have been a little more than 8.5 minutes, but it's about how long it would take to really kind of wolf down a lunch if you're in a big hurry. So these are very familiar timescales, because then if we talk about the distance across our solar system, we can look at the planets, the other orbits of the orbit of our other planets. And so the outer planets, Jupiter, Saturn, Uranus, and Neptune, are much farther out from the sun, very different worlds. I'm not going to talk so much about planets today, so I'm just going to talk about the solar system kind of as the system of planets and other stuff in orbit around the sun. But if you want to talk about light travel time, the distance from one side of our solar system to the other, sort of from one side of Neptune's orbit to the other, is about 8 light hours. So that's another kind of familiar period of time. 8 hours is a good night's sleep. So that's how long it takes light to travel across our solar system. So if you can imagine light from one side of Neptune's orbit leaving as you go to bed, and as you wake up, you can imagine arriving at the other side of the solar system. So those are pretty reasonable scales. But let me kind of bring things around, because those are kind of characteristic of interplanetary scales, the distances between planets. But stars, it turns out, are much, much, much farther away. So I'm trying to turn things around so that we can look toward the nearest star to our own sun. So the sun, of course, is the star nearest Earth, but the star nearest the sun is Alpha Centauri. And I went to completely the wrong part of the sky to check it out. At any rate, Alpha Centauri is about 4 light years away. So I'm finally getting over here. And it's this star here in the kind of middle of the screen now. So if you want to think about interstellar distances as compared to interplanetary distances, it's a difference between a good night's sleep across the solar system and a high school or college education if you think of 4 years to travel to the nearest star. So instead of imagining going to bed one night and waking up the next morning, imagine starting your freshman year of high school and then graduating and starting your freshman year of college. That's the kind of time frame we're talking about to get from one star to the next. Very different experience. Still a human experience, but a very different period of time. Well, we know, and although I said I'm not going to talk about planets so much, I will mention that we have, of course, explored our solar system. So let me go ahead and put up the trajectories of some of the spacecraft that we've sent out into the universe around us. I displayed the Voyagers 1 and 2, Pioneers 10 and 11, and New Horizons spacecraft, the 5 fastest spacecraft we have sent out into space. These are all traveling fast enough to escape the sun's gravity. So we'd say they are traveling at escape velocity. Eventually, they will make their way to the stars. But I want you to look. So New Horizons is this one, the shortest of the trails. And it was launched in the early 2000s. Let's ignore that one for the moment, because the Pioneer 10 and 11 Voyagers, sorry, that was 11, Voyagers 1 and 2 piled up on top of each other. Those were all launched in the 70s. So that means that they have been traveling for, give or take, about 50 years. So you can see how far they've traveled in 50 years. They've traveled about the same distance, because we know that Neptune's, the distance across Neptune's orbit is 8 light hours. No, these have traveled maybe about the distance light travels in a day, the most distance of these objects. So our robotic spacecraft, which have done an amazing job exploring our solar system, haven't made it that very far out into the universe around us. Instead, we understand the universe around us by studying light from these distant objects. And so basically, everything that we're going to talk about for the rest of the program is something we've learned by studying light from these distant objects, whether they're stars, or eventually we'll talk about galaxies and other objects in the universe. So we're going to brighten the sun and make it the same brightness as some of the familiar constellations in our sky. If you happen to recognize Orion here, emerging from the top, the 3 stars in Orion's belt, 4 stars in a rectangle around it. You can also see the Hyades, this little V-shaped cluster of stars, and the Pleiades, this clump of stars that's kind of moving to the lower right. I'll try to point those out later as we travel farther from home. And what I'd like to do now, though, is just keep pulling away. And now the constellations will just barely begin to shift. First of all, you'll notice that the star Aldebaran, which is a bright star that's not actually part of the Hyades. It's part of that V shape that forms the head of Taurus the Bull, but it's actually a little bit closer than the cluster of stars that forms the Hyades. All of these stars begin to shift. We've now traveled the same distance light would travel in several years, in just the few seconds I've been talking. And we're beginning to see the differences in stellar distances, because these stars, although they all kind of look like they're flat connect the dots pattern in our sky, are in fact situated in 3 dimensions. And we can see that in interstellar space, we're surrounded by this scattering of stars. One of the things I just want to mention quickly is that we know that many of these stars, in fact, most of these stars, if not all of these stars, have planets in orbit around them. We know this by, again, studying the light from distant stars. There are a couple ways we can do this. We can look for changes in the brightness of a star as a planet passes between us and the star. We can look for changes in the spectrum of the star, the sort of the color fingerprint of a star as a planet tugs on it. And those different techniques have revealed the locations of literally thousands of planets in orbit around other stars. So if we could put a circle around each of those stars, so this isn't each planet, but each star that has at least one planet in orbit around it. Some of the stars have many planets in orbit around them. Then we would see this collection of objects relatively close to home that all have planets in orbit around them. All of these stars have planets in orbit around them. The circles just kind of indicate where those stars are. The circles decrease in size with the distance of the star. So you can see on the lower right, there's a large collection of small circles, which means distant stars with planets in orbit around them. You'll notice that they're all kind of clumped in one part of the sky. That's because the Kepler telescope observed that part of the sky for a period of years and was able to make measurements of, again, thousands of stars with planets in orbit around them. So this is really kind of exciting when we think about it. When we think about, for those of us who grew up watching Star Trek, you can imagine traveling from one star to another, visiting planets and visiting life forms. And if you think about life in the universe, you can really only imagine it with a planet. And so knowing that there are thousands of planets out there is a really exciting discovery, even though, first of all, many of these planetary systems are very, very different from our own solar system. We haven't really found any planets quite like Earth. And the other kind of bit of bad news is without Star Trek's warp drive, these objects are quite far away. So going back to light for a moment, another form of light that we use for communication is radio, or at least historically we have. Now, of course, we have lots of fibers that connect us to watch television and stream Netflix and such. But historically, if you wanted to watch TV, you'd tune into a station that was broadcast over radio waves. We'd drive, still listen to radio perhaps in a car as you're driving to work. Those radio waves are a form of light, and they travel at the speed of light. And some of those radio waves are strong enough to escape Earth's ionosphere. That's sort of a ionized, as the name suggests, part of Earth's atmosphere that can block a lot of radio emission. So if we could imagine how far since the beginning of our sort of technological journey of transmitting these signals out into space, if we could imagine how far those signals had traveled, we could put up a sphere that represents, centered on the Earth, that represents kind of the outer limits of those radio transmissions. Well, the thing is that, like Marconi or whatever in the more than a century ago, those radio signals were not strong enough to escape the ionosphere. So it wasn't until the invention of television, radar, and actually the detonation of nuclear weapons in our atmosphere that we created signals that were strong enough to escape the ionosphere. So this sphere is about 85 light years in radius. So it's about 170 light years across, because the first strong signals emitted by Earth were emitted back in the late 30s, early 40s. So you can think of this as our electromagnetic footprint in the universe around us. Now, when we looked at the Voyagers 1 and 2, the Pioneers 10 and 11, and New Horizons, those are the fastest, like nuts and bolts objects that we send out into the universe. But this sphere, centered on Earth, 170 light years across, represents our footprint of radiation that we've emitted out in the universe. And you can imagine, in the same way that Jodie Foster was looking for signals from other civilizations in the film Contact, if there were radio astronomers on one of these planets inside the radiosphere here, and if they pointed their telescopes at Earth, and if they caught one of our signals, and if they interpreted it correctly, they would know that there's life on our planet. So that's kind of good news. I mean, there are a lot of circles in there. The bad news is that all of these circles with representing stars that have planets in orbit around them, each one of those that lies outside of this, as we nicknamed it, radiosphere, each one of those that lies outside this sphere of electromagnetic influence, even if there were an intelligent Jodie Foster radio astronomer looking back at Earth, she wouldn't be able to detect anything because the light simply hasn't had enough time to reach her telescope. So When we think about life in the universe, when we think about the potential of finding extraterrestrial life, the traditional means that we've used to look for extraterrestrial civilizations have their limits. The good news, and as the Kepler field of view begins to move back into frame in the lower right, the good news is we've found thousands of these planets, and we begin to study the light from these stars and potentially the light from the planets in orbit around them to begin to understand whether any of those planets have life. Perhaps not technological life, but some form of life that can change the atmosphere of a planet, much like life on Earth has changed our atmosphere. So all of these circles simply represent what we know today, the locations of extrasolar planets, planets around other stars that have been mapped by our various missions. We have a lot more exploring to do, and we have to study each of these objects individually to begin to tease apart what we can learn from their light to understand whether life exists somewhere other than on Earth. Well, as we pull far enough away, I'm going to go ahead and get rid of our extrasolar planet locations, and I'm going to keep our radiosphere displayed because we're now going to travel through, and this is an actual map of the 100,000 some odd stars that are closest to Earth. We now know we have a better map that has many more, but for our purposes, this is good enough. And we're going to travel so far that we can begin to see the sort of city of stars in which we live, although the city of stars in our case has hundreds of billions of inhabitants, hundreds of billions of stars inside this gorgeous collection of stars, the Milky Way galaxy. And you can still see our radiosphere. You can also maybe hear my cat in the background. Sorry about that. You can still see the radiosphere, this small collection of points. That's our technological footprint in the universe around us. That's as far as our radio signals have traveled out into the universe, because the Milky Way galaxy is about 100,000 light years across. And if we think about 100,000 years in terms of human history, 100,000 years ago, our species hadn't even left Africa. So now, instead of thinking about a quick pause in conversation, a quick lunch, instead of thinking about a good night's sleep or a high school or college education, or even the technological history of our species as represented by this 170 light year diameter sphere, now we're talking about the history of our species on the planet. And it's only going to get more mind-bending. And that's in terms of light travel time. And again, light, which I don't think I mentioned, is the fastest thing in the universe, traveling at 300,000 kilometers per second, 186,000 miles per second, still takes 100,000 years to go from one side of our galaxy to the other. You can begin to see a few of our satellite galaxies, including the Large Magellanic Cloud, and these other kind of red points that are in the distance represent the locations of individual galaxies. Some of those are as big as the Milky Way, with hundreds of billions of stars. Some of them are even bigger. So every one of those dots represents a collection of stars, just like the collection of stars in which we live. And as we travel farther from home, we can begin to see, and again, this is a real map. We've mapped the locations of these galaxies. There's error bars and such, but we know where these objects are. And what's interesting is, and you can see this immediately, the galaxies aren't sort of uniformly spread out through the universe. Instead, they're kind of clumped and clustered together. And this is a pattern that emerges as we look at the about 30,000 galaxies relatively close to home. This is a map that was put together by dozens of astronomers working over a period of decades. You can actually see the Virgo cluster as this large clump of dots in the upper middle of the screen. Our closest supercluster, well, really we're part of this large supercluster of stars, of galaxies. But this map was put together by dozens of astronomers working over a period of decades, carefully measuring the distances to these individual galaxies. But about 20 some odd years ago, we started to automate that process. I'm going to fade up several different surveys that are combined to give us a look at how many galaxies are out there and what their distribution looks like. And I apologize because I know at this point the things start to slow down with our live transmission because this is a complicated image. So I'll try to slow my movement to make sure that you can see this sort of with continuity. But this map of galaxies is sort of mind-blowing because by automating this process to locate and measure the distances of galaxies, we've mapped hundreds of thousands of galaxies, actually now millions of galaxies. And that map, that three-dimensional map, is continuing to grow day by day as we make more and more measurements to more and more distant objects. The color coding here, by the way, the warm color is a kind of yellowish color, is where the distribution of galaxies is densest. And the cooler color, the bluish aqua color, is where the galaxies are there, but they're sort of less densely clumped. And what you'll immediately notice is it looks like the universe is sort of shaped like a bow tie. Basically, that there are these regions where there aren't many galaxies, that there are these empty spaces. And that's not because there are no galaxies there. It's because those are parts of the universe that we are still mapping. So what you should pay attention to is the kind of the structures that we see inside the sort of the parts of the bow tie, the wings of the bow tie, because that's where you can see that clumping and clustering of galaxies. You can think of these as sort of like core samples looking out into the universe. And like a core sample that you take in the Arctic will take you on a journey through time from the layers that are closest to the surface back into the past to the layers that are farther down. As we look out into space, we are also looking back in time. So these core samples into the universe are looking at galaxies farther and farther away, farther and farther back in time. And what that means is that simply by looking out into the universe, we can see the history of the universe played out in front of our eyes. When we look out into space, we look back in time. So when we observe these distant galaxies, we're actually seeing them as they were billions of years ago. Now, our universe is about 13.8 billion years old. And these galaxies are, in fact, these individual points actually represent not galaxies, but the bright cores of very young galaxies that are very actively forming stars early in the history of the universe. We call them quasars, and we don't see them close to home because the universe doesn't make stars like it used to. These are the kind of objects we only see in the distant universe. But as we pull far enough from home, I'll try to move the camera. Again, I'm trying not to move too quickly because it all kind of becomes a slow frame rate movie here. But eventually we should be able to see, as we get to a better viewing angle, the backdrop to all of this. And it kind of blends in the way we're showing this with the color of these dots. But let me go ahead and spin these around. I'm going to go ahead and just do it quickly so that you can see this pattern not obscured by these beautiful little circles. And this pattern is that cosmic microwave background that I mentioned at the beginning of the show. You can see it most clearly here in the kind of the top slightly to the right, the bottom slightly to the right, in the space between the knot, around the knot of the bow tie. And this cosmic microwave background is the oldest light we can observe. It dates back to when the universe was only a few 100,000 years old. So the universe is about 13.8 billion years old. This is when the universe was very, very young. It emitted this light, and it's been traveling this whole time waiting to be collected by our instruments. And this picture isn't quite like, say, the picture of the moon or the picture of the Earth that I showed at the beginning of the show. Instead, this is more like a heat map. It's showing the temperature of the early universe. And this bright region, for example, corresponds to a hot part of the early universe. And these dark regions correspond to cool parts of the early universe. Now, as it turns out, the cooler parts are a little bit denser and the hotter parts are a little less dense. And the difference between the coolest part and the hottest part, or the densest part and the least dense part, is only 1 part in 100,000. So this is a tiny fluctuation. We've cranked up the contrast in this image. It's a tiny fluctuation in the distribution of matter in the early universe. And through the action of dark matter that I haven't even mentioned, in time, this tiny variation in temperature and density formed the clusters and superclusters of galaxies we see close to home, and in fact formed stars, planets, and things that are important for life in the universe. So, before I take us home, I want to note one thing. It looks like we are at the center of the universe because we're in the center of this three-dimensional image that I've been showing to you. But that's not the case. As far as we know, there is no center to the universe, and it's not that we are at the center, certainly. And in fact, although I know individuals who are inclined to think of themselves as the center of the universe, in fact, again, the universe does not seem to have a center. So the reason that we appear where we do is because we're the ones drawing the picture. We're the ones who are plotting the distances of these individual objects away from our observation point. And because of that, we end up at the center because we're the ones drawing the map. And this map isn't just like a three-dimensional map. In a way, it's a four-dimensional map. It is three-dimensional because there's the three dimensions of space that we're illustrating, but we're looking back into time as we look to more distant objects. So in a way, this is a space-time map where we are at the center in the here and the now, and the cosmic microwave background, 13.8 billion years in the past, very far from home. So with that, I'm going to go ahead and take us back home. And as I do, we're going to fade out the cosmic microwave background. I'm sorry it's going to get a little choppy as we sort of hit the pedal to the metal here. Take us through our map of hundreds of thousands of galaxies, billions of light years from home, through the various catalogs of galaxies, including the 30,000 galaxies close to home, the Virgo cluster kind of moving off to the left-hand side of our image. Each one of these dots, again, representing the location of an individual galaxy that may be as large or even larger than our own Milky Way galaxy, which will come into view shortly. Our own Milky Way, with hundreds of billions of stars, is our home in the universe, a collection of stars, gas, and dust that could be the entirety of a program in and of itself. We'll go ahead and see the radiosphere as we get close to home. I'm going to go ahead and fade the radiosphere off. Remember, this is our sort of technological footprint or in the universe around us. I lost there we are. We'll turn the radiosphere off, though, as we move through the thousands of stars closest to our own star, the sun, which is so faint that even though we're getting closer and closer to it, still not really discernible at the center of the screen. But as it comes into view, we'll actually see it at its full glorious brightness before we fade it down to reveal the orbits of the planets and the trajectories of those 5 fastest nuts and bolts objects, the Pioneers 10, 11, Voyagers 1 and 2, and New Horizons spacecraft. As we go ahead and fade those down, we'll see just the orbits of the 8 planets in orbit around the sun. And if I've navigated correctly, we'll be heading right back home toward Earth, the third rock from the sun, the third planet out in our solar system, the only place where we know life exists, and the place from which we are broadcasting this live stream. So with that, thank you for joining us for this tour of the universe that we do once a month here on the California Academy of Sciences YouTube page, as well as Morrison Planetarium Facebook, Cal Academy Facebook, and OpenSpace YouTube. We're going to put in the chat information about downloading OpenSpace. If you want to take a look, pretty much everything you saw here is built into the software. You can download it, and with a computer that has a decent graphics card, replicate this tour of the universe on your own and do even more exploring with this amazing open source software. So thanks again for joining us for our tour of the universe. Hope you have a great afternoon, and we'll see you next month.